Hi, today we're going to talk about HTTP2. We're going to have a look on a brief history. We're going to see the new feature that HTTP2 provide. Then we're going to see how HTTP2 work on the wire. And then we're going to talk about HTTP2 performance. SPDY was an experimental protocol developed at Google and announced in the mid-2009 that has the main goal of improving HTTP1. Fast forward to 2012, and the new experimental protocol was supported in Chrome, Firefox, and Opera. And a rapidly growing number of sites, both large like Google, Twitter, and Facebook, and small, were deploying SPDY. In 2015, HTTP Working Group delivered an official HTTP2 standard that was based on the lesson learned from SPDY. The coalition of SPDY and HTTP2 enabled server, browser, and site developer to gain real-world experience with the new protocol as it was being developed. As a result, the HTTP2 standard is one of the best and most excessively tested standards right after release. Before we jump into the new feature that H2 provides, I have to mention that no changes were made to the functionality or core concepts such as HTTP methods, statute codes, URI, and HTTP header fields. Nevertheless, if you're a network security engineer like me, I feel like it's important to understand how the low-level changes addresses the performance limitation of the previous protocol. Finally, even though H2 does not have to set on top of TLS, all major browsers only support H2 over TLS, version 1.2 or higher, using the ALPN TLS extension that we're gonna see later. So the first H2 feature that I want to present is the ability to multiplex requests and response thanks to the new H2 binary framing. Before we dig deeper in that, let's see how H1 suffered from the lack of multiplexing. Here we can see a client wanting to have a CSS and a GS file. Unfortunately, with H1, the request for GS can only be sent after receiving the CSS file. There is no multiplexing, i.e., only one request response at a time is allowed on a given TCP connection. The web developer community created and popularized a number of workarounds to this major limitation. We're going to highlight some of them here. First, instead of just opening one TCP connection and sending all HTTP requests one after the other, why not opening multiple TCP connections? In practice, major browsers open 6 parallel connections. Why 6? The number is based on a collection of trade-offs. The higher the limit, the higher the client and server overhead, but at the additional benefit of higher request parallelism. For some websites though, 6 is not enough. And that's where domain sharding comes into play. By splitting the website's asset across multiple subdomains, we can extend the number of concurrent TCP connections. On the other hand, we have concatenation and splitting. That is where you combine multiple GS or CSS file into a single file. That's for concatenation. Or multiple image file into a single composite image, and that's for splitting. Even though we improve performance by reducing the protocol overhead induced by requesting all those files separately, there is a significant negative impact on cache, because let's say we just update one small image of the big composite image, this will invalidate the whole composite picture. Plus there is an extra application complexity, for example, one extra CSS for managing sprites. Finally, both the GSS and CSS are passed and executed only when the transfer is finished, potentially delaying the execution speed of your application. And finally, we have request pipelining. This allows the client to send multiple requests one after the other without having to wait for each response before sending the next request. While this might sound very beneficial, and it is for some cases, but due to the fact that all responses have to come back in the same order requests were sent, this feature may cause some problem. namely a single slow response may block all response behind it. Another problem with this is that if the second response is ready on the server side while the first is still on process by the server must buffer the second response until the first is sent to the client, which may exhaust server resource. Also, failed response may terminate the TCP connection, forcing the client to re-request all subsequent resources, which is too bad. Before we move to the next slide, I would like to emphasize that these techniques are just workaround for existing limitation in the HTTP 1.1 protocol, and finding the right balance among all of these criteria is very hard. Okay, so since HTTP2 allows multiplexing request and response, we will see that most of these workarounds are no longer needed. The new H2 binary framing layer is the source of all performance improvement. This is what enables full request and response multiplexing by allowing the client and the server to break down an HTTP message into independent frames, interleave them, and then reassemble them on the other end. This also resolves the head-of-line blocking problem found in H1 and eliminates the need for most of the workaround we discussed before. Here we can see a typical H2 communication on the wire. First, notice that there is only one TCP connection that carries bidirectional streams. Each stream has a unique identifier, which can be even if it is created by the server, odd if it is created by the client, with ID 0 being reserved to the connection itself. And each stream is used to carry bidirectional messages. Each message is a logical HTTP message, such as a request or a response, which consists of one or more frames. The frame is the smallest unit of communication that carry a specific type of data. Example, HTTP header, message payload, and so on. Frames from different streams may be interleaved and then reassembled via embedded stream identifier in the header of each frame. In short, we can say that H2 breaks down the HTTP protocol communication into an exchange of binary encoded frames, which are then mapped to messages that belong to a particular stream, and all of which are multiplexed within a single TCP connection. Because with H2 all responses are interleaved, stream prioritization gives the client the chance to express in which order it would prefer to receive the responses. The client can express stream dependency, meaning I would like to receive response from stream D before any other responses, like we see in the diagram, and stream weight for setting priority between streams that are on the same level. In the diagram you can see that stream A and B are on the same level, and they have respectively 12 and 4 as weight, which means that the server is supposed to spend 3/4 more resources on serving stream A than on serving stream B. Note also that stream dependency and weight express a transport preference only, not a requirement. While it might seem counterintuitive, this is the desired design. We do not want to block the server from making progress on a lower priority resource if the higher priority resource is blocked. Flow control is a mechanism to prevent the sender from overwhelming the receiver with data it may not want or be able to process. The receiver may be busy, under heavy load, or may only be willing to allocate a fixed amount of resources for a particular stream. You might think that this is what TCP flow control does, but since TCP flow control is done at the TCP layer, it is not granular enough to regulate the delivery of individual stream. This is why H2 provides flow control at stream level. Flow control is directional. Each receiver sets a window size, which is reduced whenever the sender emits a data frame and incremented via a Windows update frame sent by the receiver. Also, flow control is hop by hop, not end to end. For example, proxy server in the middle may have a fast downstream and a slow upstream connection, and wants to regulate how quickly the downstream delivers data to match the speed of the upstream to control its resource usage. Finally, H2 provides the simple built-in blocks of flow control and defers the implementation to the client or the server. This is why we say that H2 does not specify any particular algorithm for implementing flow control. Server push is another feature that H2 provides. When the client sets up a TCP connection, receives the HTML file, the server already knows which resource the client will require. The idea here is to say, why not make the server sending them along with the first response? In H1, the way we accomplish this kind of idea is called resource inlining, in which different resources were directly embedded into the original HTML file via the appropriate HTML block, like the script block for JS files. But the server push is an improvement of the H1 inlining, because the pushed resource can be cached by the client, which couldn't be done in the previous version. Also, the pushed resource can be reused across different pages, can be multiplexed alongside with other resources, can be prioritized by the server, and most importantly, can be declined by the client. If the client doesn't want the pushed resource because it already has it in its cache, it can say, I don't want this. So here we can see an example of a server trying to push script.js file and still.css file to the client. So it is done by sending a push promise frame to the client, which contains only the HTTP header of the promised resource. The client can then either accept the stream or decline it via reset stream. With HTTP 1, headers are always sent as plain text, which adds hundreds of bytes of overhead per transfer. HTTP 2, on the other hand, compress request and response header metadata using the HPACK compression format, encoding header via a static Huffman code. Not only that, but it also indexes headers that were already seen in the communication. Indeed, accessing a web page and its dependent object involves many requests. This number commonly reaches into the hundreds for a single web page. The thing is, these request response tend to have extremely similar header. That's why both the client and the server maintain and update an indexed list of the previously seen header field with HTTP2. If at a given time the index table looks like this, and the client wants to send the same header, he would only have to send the indexes of those headers and not their name and their value. The reality of HPACK is much more complicated. There are actually two tables maintained on each side of the request or response. One is dynamic table created dynamically in each connection. One is a static table made up of 61 most common header names and value combination. For example, method get is in static table at index 2. The static table is defined to be 61 entries long. If you want to know more about HPACK, you have RFC 754. Now that we've gone through the major new feature of H2, let's have a look on how an H2 GET request looks on the wire. We're going to use the ng HTTP tool. This command line sets the window size to the power of 14 minus 1, adds an arbitrary header, and asks to download assets such as stylesheet, images, and script file linked to the downloaded resource. First, we can see that H2 was successfully negotiated. Then the client sent the setting frame right away, not the use of stream ID 0 for the connection level information. And finally, we see the content of the setting frame, namely the maximum current stream and the window size that we set in the command line. In order to doubly confirm to the server that the client endpoint speaks H2, the client sends a magic octet stream called the connection preface as the first data over the connection. The point of this string is to cause an explicit error if by some chance the server or some intermediary did not end up being able to speak H2. If a well-behaved H1 server received the string, it will not accept it. and will send an error. This magic octet, we don't see it in the ng HTTP tool, but nonetheless it is the first request sent by the client. Not the client and ng HTTP send the end header and the end stream flag. This tells the server that there are no more header coming and to expect no data. That's because this is a GET request. If it were a POST request, for example, the end stream flag wouldn't have been sent at this time. Notice also the added header, header 1 with the value foo that we added in the command line. Here we can see that the setting frame received from the server by the client, which contains different options like the maximum concurrent stream, the size of the header table, the initial windows, etc. And then we exchange acknowledgement of those settings. Here we receive a header frame from the server. Notice the stream ID of 1 indicates which request this header is associated with. We received a 200 response, which is great news. Note also that the flag end stream was not set because there is frame data to come. At last we got the data from the server. You see 5 data frame come down, followed by the Windows update frame. The client indicates to the server that it consumes 10,915 bytes of data frames and it's ready for more data. Now that the client has the base HTML file, it can start asking for objects on the page. Here you can see 3 new stream ID with ID 15, 17 and 19 for state-sheet files and icon file. And he can ask for those files simultaneously thanks to the multiplexing and the binary format, of course. Here we can see the client receiving the various header frame for the previous stream IDs. We can see various Windows updates, including a connection level update for stream 0. We see the last data frame from stream 1. And finally, we see the go away frame, which is a polite way to tear down the connection. Let's talk about H2 performance. Here we can see a comparison of how fast 100 small pictures are loaded with H1 versus H2. Without any doubt, H2 was faster. And if we take a look at the network waterfall, we can clearly see that with H1, the client was sending only 6 requests in parallel each time, while in H2, all requests were sent at the same time. Now we are going to talk about one of the major H2 limitations, which is related to the fact that H2 sits on top of TCP. We have a client that wants to send 2 HTTP requests, a GET and a POST. Because H2 allows multiplexing request and response, both requests can be interleaved inside the same TCP connection. Let's say, for example, that the GET is split into 4 packets, while the POST request is split into 6. We also assume that TCP segment is 10 of those individual packets. Suppose that all packets are correctly received by the server except one that you see in the diagram. At this point, all packets of the POST request are received, and theoretically the layer 7 HTTP2 server can start responding to this request. Unfortunately, TCP doesn't know about our POST or GET request. For TCP, all 10 packets need to correctly be received before giving them to the upper OSI layer. That is what we call the head of line blocking problem at the TCP layer. The TCP stack will wait for the client to send the missing packet before handing the 2 requests to the HTTP2 and unnecessarily delaying the response to the POST request. To see how far this limitation impacts the performance of H2, Mr. Homan used web page test to measure the document complete time of his web page, which consists of 110K images. The blue dots represent the result of H2 and the oranges represent the result of H1. In the upper left corner is the result with 0% packet loss. On the right, the upper right, you can see the result with 0.5 packet loss. In the download down left you have the result with 1%, and in the down right you have the result with 2% packet loss. The more we add packet loss, the worse HTTP is compared with HTTP 1. Mr. Human explained that by the fact that with H2 we are replacing 6 TCP concurrent connection with a single TCP connection. On the left you can see TCP congestion window, which is one of the factors that determine the number of bytes that can be sent by the server at any time, and is a mean of stopping a link between the sender and the receiver from becoming overwhelmed with too much traffic. However, when we inject 1% packet loss to that same TCP connection, here how the congestion window will look like. If we compare with H1, which opens 6 concurrent TCP connection, even if we had the same 1% packet loss on each TCP connection, the sum of the congestion window at any point across all concurrent TCP connection will always be bigger than any of those. This is why the next HTTP version, HTTP 3, will set on top of UDP and not TCP with the introduction of the QUIC protocol. I hope that I have shed some light on this topic for you and made you want to learn more about it. If so, you can have a look on those excellent references that helped me make this video.